current mechanisms giving us the efficient solution. And I don't know if we can compute what's that efficient solution. That's the problem. That's the whole debate between central planning and markets, and that becomes like a religious debate almost. The whole point is like, if you can compute that, what's the efficient solution, why would you use a market? You could just implement it. That's it, right? So the whole point is that maybe you don't even know. Tricky. Very recently, Jean Bushnell asked this question in the US. In the US, there are some markets that use capacity payments. There are capacity markets. Basically, you get paid for energy, but you also get paid for being there. It's like if when you go to buy potatoes, you pay the farmer for you pay the farmer for the tomato, but you also pay the farmer for having a farm. Like, you know, it's weird, it's odd. And I think electricity markets are the only markets with those mechanisms. So the question they asked was, okay, capacity markets are doing something. They're incentivizing some investments. Are those investments efficient or not? So the question is not whether they're doing something or not, is whether what they are doing is efficient. Is there a cheaper way to achieve the same? Basically, that's the question they have. So thanks for the point you made. It's a very important point. All right, so I just wanted to say something to finish this first section. Think of market design more as a journey than a destination. Market design is something that you do over time. You keep fixing markets, you keep improving things. It's as we talked with Alexandre earlier, it's a dynamic problem. It's not a static problem. It's not something you fix now and then you forget about it. No. It's like you have to keep improving things over time. All right. So now we get to the technical thing. Now you're going to see equations. I hope I don't grill you with all the math and everything. I tried to put here the most important stuff. That's it. Okay. But we're going to see equations and a couple theorems. Not we're not going to prove anything, but I hope you don't hate me for that. So the first part was more like motivational, right? More conceptual. This is more technical. Okay. So the basic tool for analyzing market is equilibrium modeling. That's where it all starts. Okay. On top of that, later you can add public policy, psychology, whatever you want. But equilibrium modeling is the first step. It all begins from there. And that's what we're going to cover today and tomorrow. Like different ways to model equilibrium in markets. Okay, so let's see what's a game first. So in order to define what's the concept of Nash Equilibrium. A game, in terms of its definition, it's defined by a tuple, like this tuple here. A game, I have a problem with this and with my students too, that in game theory and mechanism design, the notation gets very complicated very easily, and it turns out that you're saying very simple things. It's like I'm taking jazz guitar lessons too, and sometimes I see a sheet with something that looks like Chinese, and then my professor, tells me, oh no, that's the song of the Pink Panther. I'm like, why it's so complicated? It's like you're saying something that is so simple, but you're using the language that looks so complicated, so unfriendly. But that's the way we can communicate these things. Okay, so we have a set of players, and we have a set of strategy sets or action spaces for each player. Each player can do something, that something is in this space, and then each player has a utility function. And the key here is that the utility that each player gets doesn't depend on what that agent does, but it also depends on what the rest is doing. That's the key for a game. If you don't have that, you don't have a game. For a game to be called a game, whatever we get from this game has to depend on the action of all the players. Otherwise, it's not very interesting, right? And if you combine all these things, you define that tuple. Okay, so Nash Equilibrium. Given a game in a strategic form, basically that tuple, a strategy profile is this vector, if you want to call it, tuple, that gives us a strategy, an equilibrium strategy for every agent in the game. It's like a set of strategies for everyone. That's a pure strategy, Nash Equilibrium, only if, basically, in words, no agent wants to do something else. Basically, I tell the agent, hey, this is what the others are going to do. What do you want to do? And if the answer of that agent is SI star, then that agent doesn't want to change his strategy. No, what I'm doing is exactly what I want to do. Like, I don't want to change my strategy. Even if you tell me what the rest are doing, I want to stick to this. If you repeat that question for every agent in the game, and no one wants to change the strategy, you have a Nash equilibrium, a pure strategy Nash equilibrium. That's it. That's the concept of equilibrium. I don't know if that's clear. Someone has a question. It's so simple to put it in words, but in math, sometimes it looks like complicated. It's very simple. No one wants to change his strategy. That's it. So people have confusions about this. A Nash equilibrium is not a strategy for one player. It's an outcome for the whole game. A Nash, if you want to try, if you want to assess if a point you have is an equilibrium, you have to give me a strategy profile for every agent in the game, not for one, for everyone. And then you can check if anyone wants to change the strategy. If not, it's an equilibrium. But you can't just give S1, for example. It's nothing. That's just a strategy of one agent. Okay, so again, in a Nash equilibrium, no agent has incentives to deviate and follow a strategy SI that's different than SI star if the other agents choose that. What?
Could you please explain if there is any difference between this definition and the definition of Pareto optimal?
I can explain that with an example. This example. So, okay, so here's a game. The nuclear arms race between North Korea and the United States. Okay, so we have two agents, N equals 1 US and North Korea. Strategy profiles. Each country can choose to play education, like to invest in education, or to invest in defense. Okay? They both have the same strategy profile. And this matrix, this table shows the outcomes of the game for the players. So if they both play, for example, defense, they both get 0 utility or 0 happiness. If they both play education, they both put their money in the education, they both get 10. If the USA invests in defense and North Korea in education, the US gets a utility of 20. Imagine that it's like the US feels like it's dominating North Korea or something like that. North Korea gets -10 because now it's vulnerable. Okay, it's a made-up game. And the other way is the same. If North Korea chooses to invest in defense, but the United States in education, North Korea gets 20 and the US has -10. Pareto optimality. Pareto optimality is are the points where basically you cannot improve the outcomes of the agents without making someone at least one worse. That defines the set of Pareto optimal outcomes of the game. Okay. So Pareto optimality in a set of points, it's like a border, right? The set of Pareto optimal points. Once you get to that point, if you want to improve the outcome of one player, you have to make someone worse. Then you got to that point. Here, the only Nash equilibrium of this game is this. This is the only point that meets that definition. And that point is not Pareto optimal. It's a Nash equilibrium, but it's not Pareto optimal. Because if these countries could coordinate, they could both be better. They could both be better. To move from here to here, they both gain 10. It wouldn't, okay? If this point was, say, I don't know, 1 and minus 5, then this would be Pareto optimal, right? But because you can make them both better, that's Pareto. This is Pareto optimal. Sorry, that's Pareto optimal. This is not Pareto. So Nash equilibrium and Pareto optimality are not the same thing, and that's important because if you remember the two welfare theorems, it says that if markets are perfectly competitive, the equilibrium outcome of the economy gets it's a Pareto optimal outcome. But this is not a perfectly competitive market. So okay, so that's it. Okay, so unfortunately, as I said, defense is the only Nash equilibrium. How do you assess a Nash equilibrium? You can do analysis on columns and on rows. Basically, you fix the strategy of North Korea, defense. Let's say the US knows that North Korea is going to play defense. So USA can choose between playing education or defense, between getting minus 10 or 0. And between minus 10 and 0, prefer 0. So play defense. So if North Korea is going to play defense, the USA wants to play defense, basically. Doesn't want to play education. And if you do the analysis the other way, you get the same answer. So then, if players play defense, no one has incentives to do something else. In this one-shot game, super simple. Okay, that's the concept of Nash equilibrium. So this problem, as I wrote here, is akin to the tragedy of the commons. Sort of, not really. But you can also set up a game and check how, for example, people use natural resources. If they are public property, people might end up overusing it because they're not going to take into account the externalities they impose on others, right? So, kind of like that. It's a similar game, it's not the same. Okay. So these games are normally used in courses of political science to explain why do countries spend so much money on defense when they never fight, right? They don't get to fight. They just buy and buy more stuff, but they never fight. The equilibrium here is to buy stuff, not to fight. Right? It's to show the other country that you're ready to fight in case something happens, but you don't really want to fight. Okay? You want to look strong. That's it. Okay. So another way to define a Nash equilibrium. Say you're proposing this as a pure strategy Nash equilibrium. This is a Nash equilibrium if you go player by player. I forgot to add for all I. If basically I ask you, what do you want to do? I want you to re-optimize your problem, given that the other players are going to do this. What's your answer? And if you give me SI star as the answer, well, that was your best answer, your best response. That's the maximum utility you get given what the others are playing. If I repeat this for every player in the game and everyone gives me the same answer that is here, that's a Nash equilibrium. Okay? No one wants to do something different than what I'm proposing. Okay? So, interpretation. In a Nash equilibrium, a star is the strategy that maximizes the utility of an agent, given that the other agents are playing SI minus star. By the way, this minus here, I forgot to mention, is just a shorthand for saying the other players. This is what the other players are playing, the others other than I. It's a simple way to write it instead of writing the whole thing without SI. It's just shorthand. In other words, this is an important term here. SI star is the best response of agent I to what the other agents want to do. It's my best response. If you give me that, I respond with this. Okay? So here's a simple game between two firms and with continuum strategies. Forget about where these utility functions came from. Just trust me that that's their function of happiness. Let's say I came up with this. Okay? These are quadratic utility functions. They are concave. Okay? Easy. Easy problem if we assume an interior solution, right? How we maximize this? We just take the first order condition, do the derivative with respect to Q1, Q2. We get two equations, two variables, set of two equations, two variables. I find Q1 and Q2. Okay? Any questions with this example? No? So forget, trust me that this is the utility function. Just don't try to think where did that come from? Just something that I came up with. But how I found the equilibrium. I just maximize what each agent wants to do. So this is important to understand here. When I look at what this agent wants to do, that agent takes the action of the rivals as a parameter. So when I do the derivative of this with respect to Q1, I treat Q2 as a parameter. Okay? It's a parameter. It's like a number. Okay? It's not Q2 of Q1. I don't see that as a function of something. It's just a parameter. So if I do the derivative of that, I get 100 minus 2 Q1 minus Q2. Okay? The function is concave. I want to find the maximum. Very easy. I do that equal to 0. And then I do the other ones. The only Nash equilibrium of the game is Q1 equals to Q2 equals 3. If anyone has any question, just let me know. No?
Isn't there a minus 1 missing in the equation?
Is there a minus 1? Could be. Let's see. Let's do the derivative of this. With respect to Q1, you get 100 minus, this is squared, right? 2 Q1 minus Q2 minus, oh, I'm missing a 1. Sorry. Good. Good that you're paying attention.
So I have to take and assume all the players' decision as a logical decision in Nash Equilibrium. Because you just said, I think the other player as a react. I can react to the other decisions. So not necessarily, my decision is going to be the truly decision. I can interact to the other's decision. But to the equilibrium to make perfect, I need to assume the other's decisions is truly a perfect decision, a rational.
Exactly. Very good point. That word, it's dynamite. I spent 2 hours in my microeconomics course talking about that. This whole tower of theory works as long as agents are rational. If agents are not rational, things get very tricky. Okay? Tomorrow, and this is very important because I think 2 or 3 of the last Nobel Prizes in economics were given to folks that show that agents are irrational. Okay? So many people say, okay, people are irrational, these models are useless. Hold on. Tomorrow I'm going to show you that there is some empirical evidence that these models are not completely wrong. Okay? So to give you a teaser, it's hard to predict what a person is going to say buy in a grocery store using this model. Like if you're going to predict if I'm going to buy this or a Coca-Cola, good luck. Very hard. Okay? If you want to try to predict how a firm is going to bid in a market, and that firm has a team of engineers and economists, that's a little bit easier. Okay? Because in most cases, the objective of the firm is actually to maximize profits. So whatever you predict, as long as your model is reasonable, probably won't be too far from what's going to happen. Predicting market behavior in the short term is easier though than predicting long-term investment behavior. Okay, that's something to keep in mind. But tomorrow I'm going to show you some curves about that. Because I get a lot of that in Chile too. Like, why are you showing this? There are 3 Nobel Prizes showing that people are irrational. Forget about this. This is a political discussion, not a technical one. Models can help you to learn a lot of things. Okay? And thanks for correcting me that. I tried to spot mistakes, but this
There's a
one.
33 for the
Okay, excellent. Thank you. Appreciate it. Okay, so that approach, doing the derivative equal to 0, fine, that works for an introductory class, but that's useless for the types of models that we actually want to solve in electricity market, where there are tons of constraints, tons of variables. There's no way you're going to be able to find an equilibrium like by hand. Okay. So how can we compute Nash equilibria for games that we actually care about, like the ones that are actually interesting, not the boring ones? So, for example, I want to consider these things like capacity and transmission constraints, intertemporal limits, risk aversions, contracts, market power, administrative control of prices or decisions. That's when things get very interesting. Okay? I'm going to show you 3 approaches to address that. This is flip. This is the first one. This is the second one. The third one. One is more than an approach to solve games. Is a way to look at games. Okay, it's think of it as a language. I'm going to teach you a new language. That's it. A new way to write the KKTs. That's it. And then maybe you can solve it. If you can't do that, maybe there are numerical ways to do it. And if you're lucky, some games can be solved using optimization. Okay, that's what I'm going to show you. Okay, first of all, I'm going to grill you a little bit with optimization here. Standard optimization problem that you can write in this format. You have your objective function. You have a set of constraints that can be written as inequalities, like this. Other are equality constraints. These are the dual variables associated to those constraints, or Lagrange multiplier, whatever you call them. And a constraint like this. This says 8x greater or equal than 0. I just wrote it the other way to be consistent with that. Okay? So this constraint actually belongs to this set, but I put it outside on purpose. Okay? Okay, so I assume here that all of these functions are nice. I can compute derivatives, they're all continuous, etc. The world is beautiful. Okay? If you remember the first order conditions, the KKT conditions, the first step to do the KKT conditions was to write the Lagrangian of this thing. So you basically take all of these constraints and you put them up here, taking into account the Lagrange multipliers. And once you have the Lagrangian, you basically don't have constraints. And when you don't have constraints, you just apply the old calculus rule to derivative equals 0 and on each direction. And that's it. On each variable, sorry. And that's what the KKT conditions are, basically, right? So you do the derivative with respect to the x variables, you get that. Complementary slackness. A constraint is either binding or the dual variable associated to that constraint is 0. That's what this constraint says. Okay? The KKT constraints are nonlinear constraints. Keep that in mind, because the dual variables are variables. These are variables, and this is a multiplication of variables. This is a nonlinear constraint. Nasty. Okay? Primate feasibility. Primate feasibility is nothing else than just copying this and pasting it there. Saying, whatever solution you give me has to at least be feasible. At least. And then you have the same but for the dual problem, dual feasibility. Okay? Those are the KKT conditions. Alright, so turns out that these conditions are necessary conditions if you want to find an optimal solution to that problem. That solution has to at least meet those constraints. Otherwise, it's not a candidate to be an optimal solution. But if a solution meets those constraints, there's no guarantee that that's an optimal solution. Okay? But then if the functions are well behaved, say f is concave and you're maximizing the other functions are convex, some are affine, then those are sufficient conditions too. So if you find a point that meets those conditions, you're done. That's it. That's the object. Okay? All right. Notation. That's old stuff. I didn't say anything new. Here's notation. This is like learning to write music. Say you have a function, this function f. Nothing to do with what I just told you. There's a function f. You have a variable x, and you want to impose these constraints on the function and the variable. X greater than or equal to 0, f of x less than or equal to 0, and the dot product between those two equal to 0. If you want to write that, there's a shorter way to say the same thing, and that is using that symbol. You just say, I want that to be greater than or equal to 0, this to be less than or equal to 0, and I want these two things to be perpendicular. It's like I want the dot product between those two things to be 0. Okay? So this replaces that. It's just notation. That's it, notation. Right? And I'm not saying anything new. And it turns out that you can also write an equality constraint using this notation. So if you have fx is equal to 0, you can say, well, then x is free because it's defined here. And you can say these two guys are perpendicular too. But this is almost irrelevant because that's already equal to 0. It's just a way to write it, to make things organized. That's it. Okay, so this is just notation. I'm not showing you anything new. Well, it turns out that if you use this notation, there's a very nice way to write your KKT condition, like to organize it. Because, for example, if you look at the primal variables on the KKT conditions, you have that x is greater than or equal to 0. Surprise here, I got rid of a beta that I had, a dual variable associated to the x greater or equal to 0. That was on purpose, so I could get this. Okay? Like, remember that this was associated with an equality constraint? Now there's an inequality. A little trick there. Okay? Mm-hmm. So you have greater than or equal to 0, less than or equal to 0, and the dot product between these two equal to 0. There is a perfect here. You can replace this with a perpendicular. Then dual variables. This has to be greater than or equal to 0, feasibility less than or equal to 0, and these two have to be equal to 0 if you multiply them. Okay. If you organize things that way, you can write your KKT conditions in this format. Right? You replace some big terms with this. Okay? They're perpendicular. All of this, all of this, all of that. It's just more compact. You're just saying the same thing, it's just more compact. So look at this. You have all these unknowns. The unknowns are the primal variables and the dual variables. And if you count, you're going to see that you have the same number of variables and the same number of constraints. Okay? These are called complementarity constraints, if you write it like this. Okay? And it turns out that if you have the same number of variables and constraints, you can find a solution to this. Okay? It's a square system. So here's the recipe that I give to my students. Okay, that was a lot of math. They're like, that's boring. I tell them, okay, just take a picture of this and put it as a wallpaper in your computer. And just remember this. That's the only thing I ask you. Anytime you see an optimization problem that looks like this, think of this. That's it. A recipe. Anytime you want to write the KKT conditions, just automatically in your mind think, it's this. That's a recipe. That's all. And this is language. Okay? Those are this is a mixed complementarity problem. This is an optimization problem. This is a mixed complementarity problem. Why is mixed? Because I'm mixing inequalities with equality constraints. If I only have inequality constraints, I just call it a complementarity problem. it becomes mixed anytime I add equality constraints, like this. Okay? Alright, not very exciting, just notation. Let's look at an example. Here I have a market. I have 3 agents that trade one good, of course, electricity. Consumers, firm 1, and oh, another mistake, firm 2. Okay, there's a price, P, that denotes the equilibrium price. So look at this. This is the problem of consumers. I'm just maximizing utility. Trust me that this is how you write the utility function of consumers. Consumers choose a demand level D. Trust me that that's the way you write the utility function. This is the happiness that the consumer gets from consuming electricity, and this is the price that the consumer pays for electricity. Okay? Then I have 2 firms that sell power. These are their profit functions, utility functions. They sell the power at price P, and these are the cost functions. So firm 1 is more expensive than firm 2. They have quadratic costs. Okay? And look, the only constraints I have are greater or equal than 0. Okay? There's nothing else. There are no capacity constraints in this example. If I go back here, look, this recipe said if you don't have any of these constraints, you only have that one, then you forget about this part. This. It's easy. You just do that one, that first kick it. Okay? So, one variable, one variable, one variable. So I have demand as one variable, production of firm 1 as one variable, Q1, Q2, 3 variables. Is there another variable? Demand of firm 1. Demand of consumers. Production of firm 1, production of firm 2. 3 variables. Am I missing a variable?
Price.
The price, exactly. There are 4 variables. Okay? So it turns out that the price comes as the dual variable of the supply and demand balance constraint. Remember at the beginning of the slides when I showed you that there was a constraint that was the sum of x's equals 0? Same thing here. Okay? And the dual variable associated to this is price. Okay? So if I take the KKT conditions of these 3 problems, I get that, basically. I'm going to go back. I do the derivative of this with respect to variable D. Yeah, price is a parameter. So I do the derivative with respect to D, I get that. Okay? I do the derivative of this with respect to Q1, I get P, price minus 2 times Q, right? I get the derivative of this with respect to Q2, I get price minus Q2, okay? And that's exactly what I have here. The KKT conditions written in some organized way. And then I have the market clearing condition that says that connects the variables of all of these agents, basically. The price is free, this is an equality constraint, so the price is free, okay? So there is a way to read this in words. Because this says either that or that has to be 0. Because, you know, when you multiply them, they has to be 0. They can be both 0, but at least one of them has to be 0. Okay? So, say the price is strictly greater than 100 minus t. What's going to happen? D is 0, right. So there is an economic interpretation of that. This is actually the demand curve. If you look, price equal to 100 minus D, and if you plot that, you get a curve that is like this, right? It says if the price is greater than what I'm willing to pay, I'm not consuming. I'm not going to consume anything. However, if that's not true, then I'm probably going to consume something. For a firm, for example, here, what is this? 2 times Q1 for firm 1. What is 2 times Q1?
Marginal cost.
the marginal cost of the firm, exactly. This says, if the price that, the market price is strictly less than my marginal cost, I'm not gonna produce, right? So you can write a sentence next to each of these constraints. They all have an economic interpretation, okay? You can, like, this is an exercise I give to my students. Write the KKT conditions, then write them in words. What do they mean? I don't care about the math. Tell me what they mean, okay? They have a meaning. Okay, if you solve this, and I hope I solved it correctly, you get that solution, okay? Does that solution make sense? This says that firm 1 is going to produce 20, firm 2 40, and the price is going to be 40. Why firm 1 produces less than firm 2? Why? Because it's more expensive, right? This is Q2 squared half, this is Q1 squared. It makes sense that in equilibrium, this guy is going to produce more, right? Intuition. So it's always good. Anytime you solve a problem, it's good to ask, does that make sense? Sure. One time I went to present the results from a model to my advisor when I was doing my PhD. And I told him, this was like my second year, and I told him, here are the results. This is what the model said. And I presented him, and he was like, oh, okay, cool. Very nice. What do you say? And I was like, what do you mean? What do they mean? Like, what does the price 50 mean? Like, why is this firm producing it? Can you explain that to me? I was like, no, we just solved, hit solve, and this is it. No. That's an inappropriate use of equilibrium model. This is only useful if you can put these things in words. If not, this is just playing with math. Yeah? This has an economic interpretation. It's very important to have. Okay, let's consider now another example, a more interesting one. Same set of firms and the consumer, except that now the government created a market. The government said, oops, we're emitting too much CO2. We need to fix that externality, and we choose to do a cap and trade program. So we're going to create a market. We don't know how much each firm pollutes actually. I mean, we can monitor it exposed. So we want firms to figure out how much they want to do it. We're just going to impose a cap on how much they can emit over the year. They are going to figure out how they distribute those allowances. So the government is going to auction permits, okay, at a price, but that price is endogenous. The price is going to be negotiated. It's not a parameter. So the government says there could be a maximum of 30 tons of CO2 in the market. That's it. How the firms are going to distribute those 30 tons? I don't know. There will be an auction, okay? And both firms are going to participate in that auction. And the regulation says each firm has to hold at least one permit for every unit of CO2 they emit. That I can monitor, okay? Otherwise, they are fined. Okay. So now how firms have to buy emission permits from the government at a price that will be determined endogenously. Let's suppose that firm 1 owns, here I made another mistake, this is flipped. Firm 1, it's like natural gas thing, okay? Firm 1 is, every time the firm 1 produces a megawatt hour, it emits half a ton of CO2. But firm 2 owns a cold unit, let's say this is flipped. So for every megawatt hour, it emits 1 unit of CO2. So firm 2 now is more polluted than firm 1. But firm 2 is cheaper than firm 1. This is kind of like what happens in reality, right? Coal is cheaper than natural gas, but natural gas is cleaner than coal. Okay? So now I have to introduce new variables. First, I need to introduce a CO2 price, endogenous. I need to introduce variables of how many permits each firm is going to have to buy. And I need to introduce the regulation into the problems of the firm. I need to tell the firms, For every unit of CO2 you emit, you need to have at least that many permits. That's the rule, that's the regulation. Okay? And consumers are the same as before. I don't do anything with consumers. So the problem with consumers is the same. They don't have to buy or sell. Okay, so I just rewrote here the problem of the two firms here again. And I put in blue what's new. This is what's old, right? This is what's new. Now they have to buy permits. That's a cost. That's why there's a negative sign there, right? I need to add the regulation there to tell them you need to have at least as many permits as emissions you produce. I define a shallow price on this, just to do the KKT conditions later. Same thing here. But now I have two markets. I have the energy market, same as before. Production equals to consumption. But now I have a market for emission permits. And that market says whatever the firms produce in terms of emissions has to be at most 30. I'm going to sell you at most 30 permits. Maybe less, but at most 30. That's not an equality here. It's less than equal. And the dual, the shallow price on this is the price of the CO2. Okay, so now I have two markets, three agents. And they are interacting simultaneously in all markets. If I write the KKT now, the KKT conditions, I have more KKT conditions now. Actually, I have three more because I have more. I have one KKT conditions associated to the new variable I introduced. 1, 2. I have new KKT condition from the market clearing constraint, supply and demand balance for permits. And I also have to add the new constraints and the shallow price. So you see this start getting bigger, okay? How do you solve this? In theory, the way you solve it is that you start like testing things. Like you say, all right, let's assume demand is strictly greater than 0. That implies that this has to be equal to 0, and then you start working. It's like playing Sudoku. If you do that and you end up in a contradiction, at some point you made a wrong choice. You have to go back and then, okay, I made a mistake. Let's try it. Let's say this is 0, and this is strictly less than 0, and then it's like trial and error. Okay, that's how you will solve it. Here I know the solution easy, so I say, okay, let's assume that there is trade in all and everything. So I have an interior solution. So that's equivalent to saying all of these are strictly greater than 0. See, if all of them are strictly greater than 0, this all disappears, and these are all equalities. So you have a system of equations, right? Many variables, as many constraints, just work your way through the system of equations. It's all linear, simple. Right? That's a system of equations. And voila, that's the equilibrium. So, okay, let's see. I have more variables now, but the ones that I care about are the production levels. So now firm 1 produces 20, firm 2, 20. If I compare it to the previous solution, without the cap and trade program, firm 1 produced 20, but firm 2 produced 40. The price, the energy price, is 60 now with the cap and trade program. Without the cap and trade program, the price was 40. Okay? So what can I say about the effect of the cap and trade program? What would you say?
Increase price, reduce consume.
Huh? Raise with prices. Okay. Okay.
That's the same thing.
What?
Just demand, but that's the same thing.
Right. Okay. So let's see. Demand it's Q2 plus Q1. Right. So demand is 60 here. Here demand is 40. So demand is less. Why do you think demand is less? Because the price went up, right? And what happens? The production is also like sort of redistributed between firms. Now, the most pollutant firm produces less. And if you compute the emissions, here you see that you fulfill the regulation, and that actually this is active in equilibrium. Like the firms want to produce just as much as the government is letting them to. So policy question. What if you implement a cap and trade program that is never binding? What happens? Huh?
It's a useless cap and trade program.
What would be the price of the carbon of the permits? Zero, of course. I'm glad you understand it, because many people and many designers in Europe did not see that. They say, oh, let's implement a cap and trade program. The problem is that they put a number that was too big here, and then you're like, oh, let's see what's going to happen. The price is zero. Effect in the market? Zero. So it only works if the number is small enough. Otherwise, it doesn't work. In California, they're having some problems with this, because they say our cap of emissions is a percentage of, say, how much we produce the year before. Okay, something like that. It's a fraction. So say like 80%. So they want to the reduced. The problem is that no one really knows what's going to happen in the future, so they plan things, and then suddenly that goes up, that goes down, and the problem is that you just implemented a vertical demand curve, and sometimes the constraint is binding, and sometimes it's not binding. So the price of CO2 emissions in California is like ching, 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 right? This is not a soft demand curve. It's not like like this. It's like, or it's binding, or it's zero. Right? So there's a little bit of market design to do here in terms of smoothing prices up. The fact that you're adding a number there, like a vertical demand curve, you're saying, or you are at the constraint, or the market is worthless, basically. And maybe a way to smooth that out is to say, well, maybe if you produce 28, the value should be higher, but if you produce 32, the value shouldn't be zero. It's still valuable, but not as valuable as if the production was 30. So like you smooth things out a little bit. That way you don't get that sort of like knife edge behavior, these constraints, like are they active or not, right? That's the problem of these models, they are dumb, right? And in practice that comes up in the numbers of equilibrium. Sorry, the outcomes of real markets. Okay. So how can you solve actual problems? This is still a thought problem. I would just solve it here. An actual problem. Here are some alternatives. One alternative, the path solver, that was written by, I believe that it was mostly microservice. But that's like the simplex of the KKT conditions. Same thing. Basically, path solver takes a set of constraints like this and gives you an answer. Uses an algorithm that's called Lemke. That it's like the simplex of mixed complementarity problems. Not very scalable. So still works. You can make it bigger, but not like million variable bigger. Like thousands variable bigger. That's it. Nonlinear solvers. Nonlinear solvers is taking the brute force approach. It's saying, okay, I have that constraint, and in reality I have this times that constraint equal to zero. So you have a set of nonlinear constraints. So you just pray, give that to the nonlinear solver, and they like, please give me an answer. Okay? Sometimes it works, sometimes it doesn't. Bilinear terms are nasty. Okay? Fortunian math transformation. If your KKT conditions are linear, there's a way to linearize that multiplication of things with some big n parameters. Okay, I'm not going to talk more about this. If you're interested, you can explore it. Okay? You want to learn more about this? There's a whole book about it, and there are many cool applications on how you can model multiple markets. Like, for example, an actual market for emission permits, an actual market for renewable energy certificates. Like, this is very cool anytime you're modeling multiple markets at the same time. It's very useful. Clearing many markets. Or like say you want to model the natural gas market clearing together with the energy market. You can use this, okay? All right, if that doesn't work, many times that doesn't work. The KKT conditions are actually kind of nasty. What was the old way professors used to find solutions? doing like iterations, right? And one trick is using diagonalization or the Gauss-Seidel iteration. Here, you never compute KKT conditions, never. Okay, so what's a fixed point? Quick, let's remember this quickly. A fixed point of a function it's a point that meets that condition, fx equals to x. That's a fixed point, right? We call a fixed point an attractor if say I start with a point x0, f of x0, and then the outcome of this I give it to f again, and then I compute f of x0, and I keep doing that. If that converges to x star, we call x star an attractor. It's not just a fixed point. It's also an attractor because it's saying if I start in some other point, evaluating that point again and again, eventually it's going to take me to x star. It's an attractor. We call that an attractor in a neighborhood B of x if x star is, if it's an attractor, we call x star a stable fixed point in B, basically. I tell you, look, if you pick any point in this neighborhood and you start from anywhere you want, it's always going to take you here if you keep like evaluating and evaluating. Okay, that's a stable point. All right. For instance, I have that function. Okay, linear function, trivial. Say I want to find a fixed point. Okay, super easy. So I do fx equal to x, find x equal to 6. That's a fixed point. Okay, that's if I can do it. Say that function is nasty, like there's no closed form solution, there's no way to evaluate it. No way to compute that this way, but you can evaluate the function. Okay, so here I'm going to use that numerical approach to find the fixed point. So say I start with x0 equals 100. So I start 100, then I do f of 100, then I do f of 100, and f of 100. And here I plotted what happens if I keep evaluating, right? Like the function eventually takes me to that fixed point, 6. So I never had to solve this. I just evaluated, and eventually found it. Okay, that's fixed point. So now you might be wondering, so what does this have to do with equilibrium? Okay, it has a lot to do with equilibrium. Because if you remember, the Nash Equilibrium defined as the best response of each agent to what the rivals are doing. So say I define that function, best response. So I define for each agent, I say, okay, I'm going to give you what the other agents are doing, and then you're going to give me an answer, what you want to do. So I give you what the rest are doing, and you give me one answer, what you want to do. That's your best response function. So there are n of those best response functions, one for each agent, right? So, and that function is defined as this, is the S that maximizes the utility of each agent. I give you what the other agents are doing, so you tell me how you're going to reply. Right? It's like a recipe. If the others do this, I do this. If the others do that, I do this. Okay, my best response. Okay, and I can define a multi-valued function like this. So I sort all the best response functions like this. The one of the first agent, the second, all of them. And if you look, I can define this multi-value function. I give this multi-value function a set of profiles, and then each of these functions take a little portion of that. So the first agent looks at what the other agents are doing and gives me an answer. The second agent looks at S1 and all the others and tells me what agent 2 wants to do, etc. Okay? It's like this. It's like a map, right? So turns out that if you a Nash equilibrium is actually a fixed point on this function. Basically, if I plug in my candidate Nash equilibrium, the response should be the same. No one wants to move away from that. Okay, no agent wants to change its position. Okay? So now you see where I'm going with the fixed point. If a Nash equilibrium is a fixed point in that function. So therefore, if I want to find a fixed point, a Nash equilibrium, I can use this. Okay? That's why it works. turns out that John Nash proved the existence of Nash equilibrium using fixed point theorems from math. It's actually very funny. Brouwer's and Kakutani's theorems, there are two fixed point theorems there that he used to say, hey, if I define a game like this and I want to find a fixed point, guaranteeing that there is a Nash equilibrium, it's the same as proving that this function has a fixed point. If I prove that this function has a fixed point, it's the same as saying that game has an equilibrium. That was his contribution. He took this guy's contributions, and it's funny because I don't remember if it was Brouwer's or Kakutani. He would show up at conferences. These are both mathematicians. And he started realizing that many economists would show up at his sessions. He was like, what are you guys doing here? Oh my God, you're contributing so much to economics. And he was like, what? No, I'm just doing pure math. And then people started explaining to them, no, dude, your theorem has been used to prove that markets have equilibrium. Like there's a Nash equilibrium again. He was like, oh, wow, cool. He wasn't thinking of that. He wrote it. All right, back to an example. So here's a game where I have two different firms. The cost functions are different, so I know that the Nash equilibriums are going to be symmetrical a priori, okay, exempted. That this is the only Nash equilibrium of this game. I computed it by hand. And now I want to see if doing fixed point iterations, I get to those numbers, okay? Okay, turns out that the best response functions in this case are trivial to compute. Basically, I do first order condition of this problem, I get one equation, and I know that for whatever strategy of agent 2, the best response of agent 1 is this. So, if Q2 plays 0, my best response is 9.5. 9 divided by 2. Right? If Q2 plays this, my best response is this. Same thing with the other agent. In general, you're not going to be able to find this closed form solution. You're going to be there. So to find a best response, you're going to have to actually solve a problem, like a big optimization. But here it's easy. Okay? So I did like a little variant of the fixed point iteration. Instead of iterating with both agents at the same time, I took turns. I say, okay, let's say agent 1 plays 0 in the first iteration. And I see what does the agent 2 wants to do given that 1 plays 0. I found a response. Then given that agent 2 is playing that, what does 1 now wants to play? And I keep repeating that, and this is what happens. Right? I find the equilibrium, but I never did KKT conditions, I never computed derivatives, I just evaluated. But for that to work, the point has to be stable. If the point is not stable, you're gonna find it. Okay? Or you'll be lucky to find it. Right? And you have to be like, you're right there. Right? Otherwise, you're not gonna find it. Sometimes games have multiple equilibria. So depending on your starting point, you're gonna get different places. Okay? Well, yeah, that happens with the other methods. Yeah. Except that with the KKT conditions, where they take you, it's a little bit more obscure. Because you just give a solver this and say, okay, solve it. And it comes out back with an answer. It's not like there is a starting point. Like it's like the solver decides like what's doing inside. There are many equilibrium points. I'm not sure if you have enough like parameters or like buttons to say, hey, let's try this other thing, so maybe you can give me a different equilibrium point. I think some solvers can let you do that, others don't. Okay? The nice thing about the numerical approach is that you can explore the space. You'll be like, oh, let's start with Q100, Q0, Q here, and maybe you can find something. Okay? So it works, and it's been used a lot. Okay? That's the old approach. And the last one, and with this I finish. The last one. I think many of you have used this without knowing that you were using it. So Mr. Paul Samuelson, again, Nobel Prize in economics, has this very popular paper where he shows how you can use linear programming to compute spatial equilibrium. If you remember the welfare theorems say market implies central planning, or central planning implies market. But they don't say it will be easy to solve. They just say it works. Right? That's the problem with some theorems. They say, oh, this will be equivalent. But when you try to write things, it's like, whoa, it doesn't work. Actually, with some problems, you say, oh, let's solve the central planning problem. And when you start aggregating things, you're like, wait, I have this dual variable here. So I have one optimization problem, I know how to do that, but I have primal variables and dual variables. How can I solve that, like simultaneously? All right, so Paul Samuelson said, watch out. Turns out that if markets are competitive, when you aggregate things, all dual variables are going to cancel. So you don't have to worry about the dual variables. You're going to be in a space where you know how to work. Basically, he said, you can give that to Cplex, and Cplex is not going to complain. It's going to be able to solve it. Okay? So his theorem says, if markets are beautifully, perfectly competitive, etc., you can solve the equilibrium problem solving a single optimization problem that maximizes social welfare, which is equal to summing the profits or the utility functions of all agents in the market. The equilibrium price doesn't show up explicitly, but they are dual variables. So you're going to find them, but exposed, like Lagrange multipliers. I insist, this seems like obvious from the welfare theorems, but if you do an example where you try to compute, you go from market to central planning with some utility function, you're going to find yourself struggling with one optimization problem, the central planner. We're going to have primal and dual variables in the objective function, and you're not going to know what to do with that. So it's a single optimization problem, but not the type you know how to solve. That doesn't, it's not very useful, at least for computing equilibrium. This is useful.
I don't know if my question makes sense, but does this work only for linear complementarity problem?
No, there are extensions, but in general the problems are pretty well behaved. Like quadratic, smooth things. Smooth things work fine. I mean, he didn't write the extension, but
does it make sense to formulate a linear complementarity problem? Does it make sense?
binary variables?
Yes.
With binary variables, you lose convexity. Once you lose convexity, prices are not unique. You're in trouble now. Yeah. Very interesting. But hard. Okay, with this I finished. So that was the equilibrium we wanted to compute before with the emission permits. Same thing. So what that theorem says is that if you sum that objective function with this objective function with that objective function, and you consider all of these constraints, you're going to get the same result as if you solve the KKT conditions separately. So I said, it's not always obvious that the shallow prices are going to disappear, the prices. Here you can see that they will, because, okay, so here there's a dual variable, annoying. Dual variable, all the price variables, annoying, complicated. You want them to go away. Okay? If you add these three, how do you know that the price is gonna disappear? Anyone? How? Supply and demand, exactly. This constraint. You know that demand has to be equal to supply, so whatever consumers pay to the firms have to be equal, so that disappear. Hey, great. Okay, but what happens with these guys? They're buying permits. That's hard.
Either the price is 0
Okay. It wasn't 0.
or E1 plus E2 equals 30.
There is active, so it's 30. Okay? But the price is still there. Turns out that, and I didn't do it here, that's why the theorem is useful. Basically, it's like you have a constraint that it's relaxed on the objective function, and there's a way to do like the backward Lagrangian, like you have something in the objective function, and you're like, oh, by the way, that's like, you can take that back down here. And then the price doesn't show up here in the objective function, and you're in the land that you know how to work. So that's if you want to do the steps of doing things. But if you just use the theorem, basically you just go and write that problem. You know, you say, I know that all those prices are going to disappear, so I just do happiness of consumers minus cost of firms, subject to all the constraints that I care about. Bam, that's equilibrium. This is central planning. A central planner doesn't see the prices, right? Just tells the firms, you together cannot produce more than 30 units of CO2. No price here. You just don't do it, period. Okay? So that's what I wrote it. That's what I came up, proposed an example where it wasn't obvious that this will cancel, because it's using the theorem is useful. It just says, just think as a central planner and just write the thing. That's it. Don't. Some also guarantees that things are going to cancel, so don't worry about that. But that's why it's useful. Okay. So I'm sure that many of you that have worked with economic dispatch problem, any planning problem that you solve as an optimization problem, that optimization problem also has an interpretation as an equilibrium of a market. You're also solving an equilibrium problem. It's just that you're not solving it as an equilibrium, you're using optimization. But it has an economic interpretation. And that's key to understand things. Okay? So this is super useful because it says, oh, we're back to what we know how to use. Commercial software. Okay? Easy. I just write a big problem, thousands, millions of variables, I just give it to Cplex, Growy, whatever is your favorite software, and deal with it. Okay? If you are in KKT world, you're very constrained in terms of how big you can make the problem, because it's very hard to solve. Okay? But they're cool. So, this is the end. Final remarks from today. Optimization and markets try to solve the same assignment problem using different approaches. It's the same thing. Okay? And market design is a field that combines elements from many different fields to try to deal with markets. And equilibrium modeling is one of the key tools to analyze markets. That's like the first tool you need to learn to analyze markets. Yeah? And there are many alternatives to solve games, including optimization. You don't have to solve KKT problems, KKT conditions to compute an equilibrium. Sometimes you can just use optimization. But the economic interpretation is that you're solving a game. You don't have to forget. All right, that's it. Here you have some references if you want to use them. We're going to upload the slides so you can download it. Maybe we can upload the slides for tomorrow too, so you can print them if you want to. All right. Okay, thank you. Any question, anything that you didn't understand? I didn't want to hold people too long because it's a lot. You can spend a couple semesters. It's a lot to see. Thank you for being patient. That's very good. Okay, any question? Yes?
About the cap and trade, the cap and trade system. You said that there's a huge problem when you have the zero and the high cost. The price is always it's zero or it's high when the condition is bounded.
Yeah.
what's the solution for this problem? You said in Europe they have this problem and they don't they didn't understand why the reason of this problem. And is there any possible solution for this problem?
Let's see.
The demand response for the cap and trade. And another question: who earns the money from the permits? The governor.
Tomorrow we're going to talk about a little bit about the government collecting money.
Okay.
Let's see. Standard price quantity. What? When you impose a cap and trade program
Yeah.
with a maximum cap, you say, for example, 100. You cannot emit more than 100 in terms of the market. You're creating a demand. Okay?
Inelastic demand.
An inelastic demand.
Yeah.
And supply could be like I don't know, something like that. Okay? So what's the problem? The problem is that both curves can move every year a little bit.
Okay.
You can have more wind than what you anticipated, in which case this might move that way or this way. Or maybe coal power plants are going to produce more than what you expected, etc. So things are going to move. And on the other hand, if you define the cap as a function of something that changes, for example, like our cap is going to be I don't know, 20% of below the emissions we had last year.
Okay.
You see, both things are not fixed parameters. Things are like moving like this.
Yeah.
And when you move those things, this is the equilibrium price of the permits, right?
Okay.
But if you start moving this thing, if this curve moves a little bit that way, the price is going to go up to like something like here, right? That creates volatility. People are very happy about it. One way to fix it that is not the most elegant way is to put a price cap and a price, a floor and a cap on the price. Okay, so you say, all right, I know that this might oscillate, but I want to make sure that it won't go below this or it won't go above that, the price. So now that gives you a little bit of that gives the investor a little bit of certainty on the prices. Turns out that doesn't work very well, because if you have this knife edge behavior, what's going to happen is that most of the time the price of the permits is going to be or the floor or the cap. Right? And that doesn't have any economic meaning. It's just like a number that the regulator came up with. So the whole point of implementing the cap and trade program was that the price was going to come out from the market, not from you. But then the price ends up being this or that, which was it's defined by the regulator. So that's not working very well. I believe that one way to do it is to smooth that curve up a little bit and to say, well, we value permits something like that. Okay? To add a little bit of elasticity to that curve and say, hey, if you want to go past our goal, that's still valuable for us. Okay, and if you don't meet it, it's not that the price is going to go up to here. It's going to have a value somewhere. One imperfect way to do that is to allow firms to bank or borrow permits from previous years or future years. To say like, hey, I'm going to owe you permits this year. I'm negative, but next year I'm going to compensate for.
So it's a long-term balance.
The excess I have this year, I'm going to save it for next year, and that way we're not going to collapse prices. So I'm going to let you create a little bit of scarcity as long as you keep those for next year. Imperfect solution.
Is it used in any place?
Yeah, it's used in California.
California uses this approach.
If you want to send me an email, I can see your cool paper by Jim Bushnell where they report this, that this is happening, and California is not very happy with it. They were like, we have this very sophisticated market. It looked great in the equilibrium models, and now we see that prices here or up here, and firms that see those signals to invest are like, well, what should I do? It's like either 0 or 100. If you're risk averse, that doesn't give you a very good signal, right? Not the signal that you want to do.
If you're doing this, you're more or less doing something like a storage of emissions.
Yeah.
Okay? If you have a storage of emissions, then you have future costs for emissions.
Yeah, it's like a value.
Yeah. And how to set this future cost? How to define this future cost into this? Because then will be a coupled in time problem. And if you have a coupled in time problem, then you have to have something like a depth cost function. How to define it?
That would be an administrative thing. It would be an administrative process, I believe. Like it will be the regulator that comes up with a number, I don't know, from probably like scientific reports on what's the cost for society of not reducing today 10 units of CO2, but reducing them tomorrow. Okay, so you need to come up with some curve of what's the cost of not doing it today, but doing it tomorrow. It's not an easy answer, it's just a proposal. They're trying to fix it. The problem with, an economist will say, look, the problem of externalities in terms of emission, you can solve it very easily. Tax, period. Just tax emissions. Done. Demonstrated in the 50s. The problem is that that's theory. Try to do that in reality. You're not going to be able to pass regulation. So that's the first best way to do it. You get to publish your paper, everyone's happy. But then for a practical implementation, you're going to find political opposition to do it. So that's why, in most cases, regulators need to come up with some alternative way to do the same thing, right? But in a way that people don't believe, like, hey, you're taxing this. No, we're not taxing it. Actually, we're creating this market on the side. Yeah, that's the same thing. I'm telling you that.
But this kind of problem happens because the supply function becomes very steep.
Yes.
At the midpoint.
Yes. It actually becomes very steep.
Yeah. Why the function has this kind of a form?
In California, they have now a lot of renewable resources. And the amount of generation available, they found that changes year to year. It's not like you can predict that the amount of wind power you're going to have every year is the same. So things are correlated. So if it's a bad year for wind, it's not a bad year for one wind farm, it's a bad year for all wind farms. And then suddenly, things go.
Okay.
And then you have to turn on
Either
coal.
a lot of wind or no wind.
It's not like there's no wind, it's just that over the year there was less wind than the previous year. And then that means that you produce more or less carbon emissions because you have to turn on coal. So if you're relying on natural resources that are variable, this is expected. You can't, it's like height. I don't know if it's very variable here, but in Chile it's pretty variable. Like, you can go from dry to very wet. You know, emissions are very different.
So you're creating an artificial storage just to
Smooth things out.
Yeah.
But it's like an engineering solution. Like, again, an economist will say, you're wasting your time. Just post a tax, $400, done, problem solved. But you're gonna have to come show up dead in a river.
Se fizesse o segundo cara ser interferido pelo
Any more questions? So, see you tomorrow, same time. Okay? Thank you guys.